Hello everybody, welcome back to our Gregorius Maths video. In this video, which is long overdue, I will be introducing a new series, the Homological Algebra series. Now, I did already start a Homological Algebra series about a year ago or so, I don't know when it was, but it was a long time ago. Hold on, let me just close the door. I did start a Homological Algebra series quite a while ago, but this one is intended to be more formal, more well planned out, that type of thing. So I will be having notes, so they are quite intended to be slightly longer videos than normal, but I think it will hopefully fit together quite nicely. It will be Homological Algebra with a look towards algebraic topology, since that is kind of a more classical perspective, you could say, and sort of the one that excites me the most. So I'm going to be introducing the series and giving a bit of motivation for why we should even be bothering about homological algebra in the first place. And I'll be introducing what I'm going to be talking about for the rest of the series. So let me firstly start off with the motivation for this, which will be the main bulk of the video. So so I'm going to talk about simplicial homology, but without actually talking about simplicial homology until the end of this video. So firstly we'll consider a simplicial complex X. So firstly we should talk about what an n-simplex. So a simplicial complex is just something that can be decomposed into finitely many different n-simplices. So we should probably talk about what an n-simplex is. So I'm not going to give out the actual definition where you would write like delta n, that type of thing. I'm not actually going to write that out. However, what I am going to write out is a zero simplex is just a point, right? And a one simplex is just a pair which would be written like this, and that's just a line between A and B. A two simplex would be a triangle with, of course, vertices A, B, and C. A three simplex, A, B, C, D, is just a tetrahedron. Is that the right word for it? Yeah, tetrahedron. And there are higher dimensional analogues called n-simplices. Okay, I might as well keep that on the board. Right, so a finite combination of these, so for example a rectangle, which is just two n-simplices stuck together, is a simplicial complex. Now, we want to study, topologically speaking, whether or not the boundary of an n plus one simplex, let's just say the boundary of an n-simplex can be written as the union of n minus one simplices. So for example, a triangle, this triangle for example, could be written as the boundary could be written as the union of AB, BC, and CA, which are two simplices. So we want to measure the extent to which this is true in any simplicial complex X. Okay, so that's quite a natural question to ask, and it turns out that homology is the best way to do so. Right. So for example, when n equals, if we were to say, so the very small dimensional case when n equals 1, i.e. can the boundary of this thing be written as just 2 points, is just path connectedness, i.e. that's just asking, is there a path connecting A and B? So this is quite a natural question to ask. Okay, let's make this process a bit more rigorous. So let's consider the boundary operator. Now, we'll consider a triangle for now, A, B, C, like so. Is that how I've done it here? Okay, slightly differently, but whatever. Okay, so, what's the boundary of A, B, C? Okay, so this is equal to AB. Sorry, I should have written this out. This is slightly different to what I've written in my notes, but okay, we'll go with the flow. So we've got AC union CB. Now the order will matter. Union BA, which looks weird. No, hold on. So, I sincerely apologise for this delay. Okay, we've got. Okay, yeah, here we go. Alright, we've got AB. This is the way to do it. BC. Okay. BC. Now the reason I'm doing this is just so that the. Now it's just because it's just a rotation, but the reason I'm being very specific about the order in which I do the union is so that the general definition, which I'll introduce in a second, becomes more natural. So it's BC, right, here we go, union CA, union AB. Here we go. Yeah, this is it. Okay, now, let's assume now that this triangle is oriented. So the direction, it does matter. And therefore, CA is literally just negative AC. So now we've got BC union negative AC union AB. Okay, now let's just use additive notation. So let's replace this union with just a plus. So now we get BC minus AC plus AB. Okay, sorry about the long-windedness, but okay, this is what we should get to. And the remarkable, okay, I won't say remarkable, but the extremely useful fact, which lends itself to homology and stuff, which if you know anything about homology, will become immediately familiar. The fact is that if we do the boundary operator twice, we indeed just get 0. So partial squared is just 0. Now let's demonstrate this for this lower dimensional case. So we'll define the boundary of BC as just B minus C. So now if we take the partial, so if we do the boundary twice on ABC, I'm being deliberately sloppy with my indices for now, but I'll be more precise in a second. So this right here will be the boundary of this thing right here. BC minus AC plus B. And this is just equal to B minus C, don't need these outside brackets, minus A minus C plus A minus B. And now if we do the algebra, this B cancels with this B, this A cancels with this A, this C cancels with this C. So we just get 0. Right, excellent. Now we want to generalize this for n dimensions, and then we need to bring in homology into this whole story in order to obviously motivate the subject. So, let's do exactly that. So we need to just get a little definition out of the way. So Cn is equal to just the linear combinations. So it's just the set of all linear combinations of n simplices on X. Okay, cool. Right, so now that we've got this out of the way, we'll define the boundary operator in general as a map from Cn to Cn minus 1. So, how do we do this? So the boundary map of some, what have I written here? Okay, I've written it in actual components. So I've written v0 up until vn is equal to. Now this sum on its own would look very unmotivated, but with this in mind, it is actually very motivated, and I'm going to use this form here to check that we've got the same thing. It's equal to the sum from I equals 0 to n, right? Yeah, I equals 0 to n of negative 1 to the power of I times v0 blah, 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 up until vi hat blah, 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 up until vn. Excellent. Now, what does this vi hat mean? This just means that we get rid of the vi. So for example, if I were 2 and n were 4, we would get v0, v1, v3, v4. So we just exclude the vi. Okay. Now this matches with our thing here, because, right, so when I equals 0, we're getting rid of v0, which is a. When I equals 1, obviously we need a negative sign, and we're getting rid of v1, which is just b, which is this. And when I equals 2, we just get rid of v2, which is just c, which is this. And obviously the positive sign, because... So this matches exactly with what we were doing back here. Right, now, it remains to show that our boundary operator does indeed square to 0 for general n. Thankfully, this is not too hard to show. Let's go with the purple, I like it. So, theorem. We have that partial n minus 1 times partial n equals 0. For all n, of course. Now, of course, we should strictly be doing this on a sum, but of course all elements are of this form, and so we'll just show that the boundary operator of something of this form is equal to 0, and therefore the sum of all of those things is just going to be 0, since this is just a homomorphism, so we can split up in that way anyway, so that's okay. Right, so, proof. So we have the boundary of n minus 1 of x0, blah blah. We'll use v since I use v in my notes, I believe. Oh, I use x in my notes, never mind, I'll use x then. x0 up until x I hat, up until xn, is equal to. Now, here's where we need to get a little bit technical. So we're going to split it up into 4 parts, just so that you know where I'm going. So, of course, firstly, sorry, 2 parts. But, okay, anyway. So firstly we have the x0 hat, blah, 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 xn, plus, da, 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 up until, x0, da, da, xi hat, xi plus 1 hat, da, 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 up until xn. And then we have plus x0 xi hat xn hat. Now, why have I split it up in this way? Well, from here to here, so that is if we have a new variable j, which is our new hat. Oh, sorry, I should have an x. I should. It should be in there, should be inserted. Anyway, so, now, so this is the 0th term. And all the way up until we get to I, this will be the jth term, for example. So xj, removing xj will remove the jth term. However, once we get past xi, because xi is removed, actually xi plus 1 is the ith term. And xi plus 2 is the I plus 1th term, and this is because xi is already removed. And thus, from here to here, we should be doing negative 1 to the power of j minus 1, because actually we've just gone j minus 1 terms, not j terms. So, overall, this will look like this will have the following form. Let me write it out nice and large. It'll be the sum over all j less than I, negative 1 to the power of j, just j, times x0 del xj hat del xi hat del xn, plus the sum over all j greater than I of negative 1 to the power of j minus 1 of x0 del xi hat del xj hat del xn. And so, because when we just flip these two we just get a negative sign, indeed it turns out that this thing right here is just the negative of this thing, and so when we add it up, okay, let me convince you here. Multiplying this by minus 1 twice does nothing. So if we multiply it by minus 1 now, what we're just getting is, what am I saying? Right, yeah, flipping these two, flipping these two is multiplying by minus 1. And so when we flip these two, yeah, we get this right here, and we're multiplying by the minus 1 to get this. And so if we multiply by minus 1 again, we literally just get this minus itself, so we get 0. And that, of course, completes the proof. So the boundary operator does indeed square to 0 for all n. And so what we've actually done here, and this is where it should definitely start to smell like, of course it's already been reeking of homological algebra before this, but if, in case you haven't got an extremely blocked nose, this is the time where it should definitely scream homological algebra to you right now. Because what we've actually done is we've created a chain of groups that looks like this. C3 of x, and then this maps to be a partial 3 to C2 of x, this maps to be a partial 2 to C1 of x, and this maps to be a partial 1 to C0 of x. And we've created a complex, a chain complex, so to speak, such that partial squared is equal to 0. Okay. Now this is a key concept in homological algebra. This type of thing is what's studied often in homological algebra. But in this case, this is a chain complex of these chains here, which are linear combinations of simplices. And so we need to use this somehow in order to study our original question, which was, can the boundary of an n plus 1 simplex be written as a union or a combination of n simplices? So, we've got the boundary map right here, so that's surely got to be involved. And I'm going to introduce a little bit more notation before I get to the meat of this argument, and that is that Zn of x is equal to the kernel of, let me just get my indices right, kernel of, partial n, and these are called the n cycles, and obviously the image of, which I'm about to define, Bn of x equal to, let me get the indices right, the image of partial n plus 1, and these are of course called the n boundaries, of course, because it's literally just the image of the boundary map. And the reason that we introduced this notation is just so that it's neater to write out the homology group, because indeed, notice by this fact here, which I'll write out with precise indices, so if we have partial n plus 1, partial n equal to 0, this is the result, right? Or is it the other? Sorry. Partial n partial n plus 1 equal to 0. Because of this, we have that the kernel, we have that the image of this map, the image is a subset of the kernel of this one. Because obviously all elements of this form just go to 0 in this map here. So we have that Bn of x is a subset of Zn of x. Okay. So now, we have that all boundaries, n boundaries are n cycles, but not all n cycles are boundaries. And indeed, these n cycles are precisely obstructions to the property that an n simplex can be written as a union of n minus 1 simplices. And so the most natural way to view these obstructions is literally just by taking the quotient, which is just the homology. And therefore we define the homology group, the nth homology group of x, to just be the cycles mod the boundaries. And so, when our homology group is equal to 0, this means that there are no n-dimensional holes. That is, the cycles are precisely the boundaries. And yeah, there's no obstruction at all to the fact that an n simplex can be written as a union of n minus 1 simplices. However, if there is a non-zero, so if there are elements of this set, then those cosets there, those non-trivial cosets, can be viewed as obstructions to the desired property. So, in general, normally in topology, but now of course even in physics, in algebraic geometry certainly, in differential geometry, cohomology and homological tools are used. And in general, what we want is that Hn of x being equal to 0, where x is, I don't know, topological space or whatever machinery you're using at the time, equal to 0, has a nice interpretation. That is some property, that statement there. This is what we want, a concrete interpretation of this. And therefore, elements are just obstructions. They are just counterexamples, one could say. They are blocking this space X from having this neat property. And so we are precisely looking at the obstructions to the nice property that we have, which is obviously a very useful thing to be able to do. And do I have anything else to say about this? Right, yeah, I've got a little counterexample for the first homology group being for being trivial. So, for example, if we look at the punctured plane, so yeah, let me do this in red. So, if we look at the punctured plane, so that is just R2 minus the origin. That is, we just take the plane and we just put a hole in the middle. Then, if then we have, so we just call this x. Then we have that h1 of x is not equal to 0. So intuitively, the punctured plane has a one-dimensional hole, which obviously we know is true because it's literally got a point in the middle, which is just been punctured. So that's obviously a one-dimensional hole. But we want to prove this rigorously, of course, and sanity check that our thing is working. So, which element is obstructing this statement from being true? Well, what do we have here? We have right, yeah, if we have A, B, C, if this is a triangle with the hole in its interior, then we have that alpha, which we define as BC minus AC plus AB is actually is a cycle, a one cycle, that is not a one boundary. Sorry, is it the other way around? No, I've got that right. Yeah, it's a cycle that's not a one boundary. And the reason for this is, well, obviously it's a cycle because it's obviously in the kernel of the partial 1 map, which, as we actually showed here, it's obviously in the it's obviously in the kernel of this map. And of course, those are all one simplices because those don't go through the origin. However, ABC, and the reason it's not an element of this image is because it's not the boundary of this triangle. Obviously, you'd have to show a bit more, but intuitively speaking, it's not the boundary of this triangle. And the reason for that is it's not the boundary of this triangle because that triangle has the hole in its interior, and therefore it can't be a two-simplex in the punctured plane. And therefore, this coset alpha plus b1 represents an obstruction to our beautiful, delicious property that that all two simplices in the punctured plane can be written as the boundary of all two simplices can be written as a union of one simplices in the punctured plane. And obviously this is a counterexample. So that's the main bulk of the motivation. Of course, topologists since have studied a wide variety of things. For example, we put coefficients into this ordeal by tensoring with the chain complex by some abelian group G, and then we call that coefficients in G. Of course, we also to take cohomology, take the dual, that is, you hom everybody here, and that turns the arrows the other way around, and that's cohomology with coefficients in G. And so we topologists do neat things like this in order to study cohomology and homology groups, and that's how it's actually used, because you might see that all the time appearing in in topological context, like, oh, we take the cohomology, we take the homology, but what it's actually doing is measuring stuff like this. It is a useful thing. There is a reason why it pops up so much. Okay, so that's the motivation out the way. Now I might as well introduce the actual series. So some of you might remember last summer. So obviously, if you're only interested in motivation for homological algebra, and not actually homological algebra, you can click off the video now, which would be very weird, but okay, yeah. Anyway, so most of homological algebra. Sorry, what am I talking about? Last summer, I began a series like this to do with homotopy theory, classical homotopy theory. And actually I was very successful in writing the notes, and I'll post the slightly unfinished, albeit, notes in the description of this video, because they are quite good notes. I should post them somewhere. I might put them on the blog. But anyway, I started a series like this. I only got 3 or 4 videos through, which is a great shame actually, because it would have been epic content had I uploaded all 24 videos. But I've decided this summer, partly to do with a project that I'm working on, which involves homological algebra, so obviously a little refresher just by doing it is always appreciated. Anyway, I decided this summer to do a similar type series on homological algebra. Hopefully this time I'll get through all of the videos. I have been a lot less ambitious this time. I've done 12 sections. Obviously this is not a fully written set of notes. In fact, I've only written the introduction. But, okay, anyway. So, the plan so far, and obviously I'll let you know in the next video if there have been any ad hoc changes, but the plan so far is introduction and motivation. Okay, that's done. That's a typical thing. Then we're going to talk about Hom and tensor, just because they come up all the time. I even mentioned them now. Tensoring the chain complex with G and homming it and that stuff. We need Hom and tensor to do homological algebra. So I'll get that out of the way, talk about the properties and stuff like that. Right, then we talk about special types of modules. These are modules that come up in homological algebra. These are special modules that we study, and so I thought I should note them down. And then I talk about categories and functors, because, of course, for pretty much all fields of mathematics that will be covered on this channel, categories and functors are needed at some point. So those first 3 videos are kind of more still building up the prerequisites, trying to get a flavour of the actual, just the homological algebra. But what's exciting about this series is that it looks towards algebraic topology as well. So it's not just focusing on the homological algebra side, we are going to be talking about some algebraic topological applications which hopefully build up intuition, should build up the kind of understanding the bigger picture. Here's where it gets nice. So then we talk about complexes, so this stuff here. This is the proper homological algebra now starting. We talk about complexes and cochain complexes and all that stuff, and we talk about singular homology, and we talk about singular cohomology as well. Now, this singular cohomology is actually a generalization of this stuff. And so it is well motivated to study singular homology. And obviously that's a very old, well, I don't want to say old, but comparatively old topological tool, singular homology. It's normally kind of a thing you'll see in an average standard algebraic topology textbook. So it'd be nice to look at that with all of this motivation behind as well. Then we'll talk about sheaves. This is interesting, actually. Sheaves, I reckon I could do this series without talking about sheaves or sheave cohomology at all. But I think talking about that stuff kind of enriches our understanding of quite a lot of different fields, especially in homological algebra. Actually, especially in algebraic geometry, which I did not get as far as I wanted to with, just because exams, and then following the exams, a lack of motivation to pick it back up. But anyway, it's not about algebraic geometry. So sheaves, very useful concept overall, and I will be using them and talk about sheaf cohomology in this series. Then I talk about de Rham cohomology, which again is building up the intuition, which it will weave all the stuff nicely together, talking about de Rham cohomology, which some people might know is very linked with singular cohomology, so, and it's also linked with sheaves as well, so again, bringing all this stuff together. And then we get again back into the more nitty-gritty, purely homological algebra stuff. We go into derived functors. And of course I haven't written these notes up yet, but hopefully derived functors, hopefully these things, I will do that with a look towards derived categories as well. So if you're interested in that stuff, then definitely stay tuned for that video. Then I'll talk about Tor and Ext. I'll see with how I'm writing these things if Tor and Ext and derived functors are short enough to be both in one video, but for safety, I've put them into 2 different videos. Now, Tor and Ext are probably the most important derived functors out there. And we'll see that they're the derived functors of Hom and tensor. And they are used all over the shop. So it's very important that we get an understanding of those. And then back to applications. So we talk about sheaf cohomology, which we do need the language of derived functors for beforehand. So that's why I've done that after that. And that'll actually be a nice non-Ext and Tor application of derived functors. So that'll be nice to look at. Then we look at group cohomology, which is actually, I know this is a look towards algebraic topology, but group cohomology is actually looking more algebraically, so it's looking on the other side of things. But it's actually a really nice way to see how homological algebra can be used in a more algebraic context for group extensions and stuff like this. And it is very commonly studied in homological algebra textbooks as well. So this is not a novel thing to introduce group cohomology near the end of a homological algebra course. And then I couldn't resist it. I am going to talk about spectral sequences for the last video of this series, but more of the nitty-gritty kind of detail rather than previous talks I've done on spectral sequences where I've kind of said, okay, modulo some problems which won't arise, we can do this. With all of this machinery having been built up, I feel now that it's a good time to talk about the actual problems that can arise in spectral sequences and the more rigorous foundations for it. And then I might do some examples that probably, maybe that would constitute another another video necessary for these spectral sequences. I'll see. And yeah, that'll be it for now. Now, another thing I should say is that my Discord server is holding Gregorius Summer, which is going well so far, so expect a Furco talk to be uploaded. It's been recorded and done. Expect it to be uploaded soon. There's also an interview, which was a impromptu interview, it wasn't planned or anything, of Furco as well, where people just, after someone else gave a physics talk, which will be uploaded onto their channel, unless they didn't decide not to upload it, but anyway, they said they would. Chris basically just got bombarded with a bunch of physics questions, which basically evolved into a physics interview with an actual physicist, which I thought was really cool. And so that will also be uploaded onto the channel. So yeah, stay tuned for those. There's also a bunch of other talks coming up. I know that, so obviously there's the Chris one that's coming up on quantum information. Then, obviously you won't know who these people are. I'll use their real names. Then Kevin will be giving a talk on number theory at some point. Stavros will be giving a talk on differential equations in Lie theory at some point. I plan to learn about functional analysis and C-star algebras, again for a project that I'm doing, but I hope to be giving a talk on what I learned by the end of the summer. Then Kasra has written up slides about categorical homotopy theory, but I'm not exactly sure what in that subject he's covering. But he's written the slides, but I will be reading them out simply because he does not have the capability to read those out, to present that talk himself. So I'll be technically giving the talk, but I will have done none of the work beforehand. And I think that George, I think is his real name, will be giving a talk on linear algebra, so a little bit more basic, but also quite interesting. I actually never properly learnt linear algebra, so that's probably going to be helpful for me. So yeah, loads of talks coming up, hopefully, which will hopefully all be recorded for this channel. So yeah, lots of content to be looking out for in Gregorius Maths, so make sure that you turn on notifications, and you subscribe, and you smash the like button. Yeah, okay, thanks for watching. Okay, yeah. Bye-bye.